and welcome all of you to this session of heat transfer. Today we shall be discussing the application of one-dimensional heat conduction equation for the cylindrical tubes. In the previous lecture we had seen how the one-dimensional conduction equation can be implemented in the cases of plane walls, and we have done some numerical problems to understand the concept in a much better way. So let us take our discussion in the forward direction by discussing the topics on the one-dimensional heat conduction in the cases of cylindrical tubes. Now, if we address the typical examples of cylindrical tubes, then we will find that in most of the cases, like in the cases of boilers, in the cases of condensers, or most of the heat exchangers, you will find that the cylindrical tubes are being applied. So we need to study the heat transfer effect in these cylindrical tubes in a much prominent way so that we can understand the heat transfer phenomena in these cases. Since this is related with most of the process industries, the study of heat transfer becomes very important. So let us carry forward our discussion and let us see how the one-dimensional heat conduction equation can. So let us consider a cylindrical tube which has a inner radius of r1. So this is your r1, and it has a outer radius of ro, or we can take this radius as r2. So r2 is your outer radius and r1 is your inner radius. Now the length of the cylinder is L. So now we are considering heat conduction through this cylinder. Now as you can see here in this diagram, the temperature of the inner wall is T1 and that of the outer wall is T2. So you can see heat transfer in the radial direction. Okay, so this is the most important point you must understand. So the direction of heat transfer is in the radial direction. So you can see from this diagram all the heat transfers are taking place in the radial direction. Okay, so if you understand that, then we can move on to the general heat conduction equation, and we will see that how this equation can be applied. Okay, so the basic understanding from this diagram is that we have considered a cylinder which has a inner radius of r1 and an outer radius of r2. The length of the cylinder is L, and heat transfer is going on in the radial direction. So let us just give me some time and I will write the general heat conduction equation in cylindrical coordinates. Mind it, in the previous cases, in most of the cases, we have written the equation for the Cartesian coordinates, but here we would apply the general heat conduction equation in case of cylindrical coordinates, and then we will see, since there is no heat transfer going on in other possible directions except the radial direction, we can neglect those. So, and you know, this is a steady state condition and there is no internal thermal energy generation. So let us see how the 3D and time dependent conduction equation can be reduced to a simple equation, simple second order differential equation after the application of that. So let us just see. I'll be writing the general conduction equation now. So in case of cylindrical coordinates, you can see that this is your general equation. Now what happens if we apply this equation in the cases of steady state heat conduction? So that suggests that this part would become 0. Okay, since it is a steady state, it means that it suggests that there will be no change in the temperature with respect to time. So this part becomes 0, and we have considered heat transfer only in the radial direction because both the ends of the cylinder are insulated, so there is no provision of heat transfer through the other two directions. So this one and this one becomes 0. Okay, and our primitive assumption was that the material was isotropic and homogeneous throughout its mass, and there was no internal energy generation or thermal energy generation. That means there was no heat source present within the control volume. So this QG, which is referred as the volumetric heat generation, this is also 0. So after applying the assumptions and understanding the facts, we can see that this equation merely reduces to this only. So just give me some time, and I will clear up all the terms which are not required here. So we can see that this equation has been merely reduced to all the terms of R. That means here you can find heat transfer taking place. We can see that the temperature is varying with respect to the radius. Okay, so this one should be removed. So we can see ultimately this equation becomes del 2t with respect to del R2 plus 1 by R del T del R is equal to 0. Okay, now what happens if we take 1 by R as common? So it will be R delta 2t del R2 plus delta t del R. Okay, so from the basic concepts of differential equation, we can easily understand that this part can be written as 1 by R into del R of R delta t del R. Okay, that means if you derive this part, you will obtain this one. So let us recheck it. So it would be R delta 2t del R2 after deriving this. Okay, after making the differentiation, so it will be R delta 2t del R2 plus delta t del R, which is exactly present here. So you can see this term can be reduced because it is 0 and this radius can't never be 0. So we can always say that this 1 by R is a non-zero term. So we can cut it off, and we will see the equation will be reduced to something like this, ddr. So previously we were writing this equation in the partial differential format. Now we can write this in the general derivative format or the general differentiation format. So we can write ddr of r dt dr, which is equal to 0. So this is our primitive equation which we have observed for the one-dimensional steady-state heat conduction in the cylindrical coordinates. Now it is quite obvious that we will like to differentiate this integrate this equation. So after performing the first integration, we can see that this will be C1. That means this since we have integrated it, this part will be a constant, and in the second part, so let us just remove this all, we can see that this dt dr will be C1 by R, and we can write this dt equal to C1 by R into dr. Okay, since C1 is a constant, the integration will take place with respect to R only, and you know that while integrating with respect to dr by R, it gives ln R. Okay, so we can write t is equal to, obviously we are taking an indefinite integration, and later on we will apply the boundary conditions to find the final or the exact solution. So t would be equal to C1 ln R plus C2. Okay, I hope you have understood it. The integration was very simple. Now let us apply the boundary conditions. Okay, so here it is taken as TO, but take T2 for better understanding, and take R2 here. So at your radius r1, the temperature maintained is T1. So if you write at r equal to r1, T will be equal to simply T1. Okay, and r equal to r2, T will be simply equal to T2. So I hope you are able to understand these facts. And now if we solve this equation, putting r equal to r1 and t equal to t1, we will find two equations have been created. And after solving this equation, we will observe that this c1 can be taken as by the help of the basic equation. We will observe that this c1 can be written as minus of t1 minus t2. This we are writing this term for the c1. So c1 can be written as t1 minus t2 ln r2 divided by r1. So I am not solving the equation for you. I am just writing the constant which you would get after solving the equation. Okay, so you can see that this c1 becomes minus of t1 minus t2 divided by ln of r2 by r1, and you will find that this c2 will become t1 plus, it will be like this, t1 plus t1 minus t2, okay, divided by ln r2 by r1 into there will be, I'm sorry, it will be ln r. Okay, it will be ln r1. So this is the value you will obtain after solving the equations for r equal to r1 and t equal to t1. And so this is your boundary conditions. Okay, so this is your nothing but the boundary conditions at r equal to r1. That means we are considering the inner radius here. The temperature maintained in the inner radius cases is T1, and the temperature maintained at the outer radius part is T2. So there R is equal to R2 and T is equal to T2. So you can generate two different or two separate equations, for which you will solve the equations for C1 and C2. And after solving the equations for C1 and C2, you will get these two values. And after observing this, since we have found out the values of C1 and C2, if we put these values in this equation, we will see that this t can be written in this format. So it will be something like this. Just I am putting the value of C1, so it will be T1 minus T2 divided by ln of R2 divided by R1. Okay, so it was very simple here. I am just putting up all the values here, and C2 will be T1 plus T1 minus T2, C2 will be T1 minus T2 divided by ln of R2 divided by R1, and here is a factor of ln R1. So let us remove these terms here, because we have generated the temperature distribution, we have calculated the temperature distribution, and let us try to simplify this equation here. Since you can see that this T1 minus T2 term is common for these cases, we can write also T1 T is equal to T1 plus T1 minus T2 divided by ln of R2 divided by R1. So this is your R2 divided by R1, and here you can see we can take this term common. So it will be like this: ln of r1 minus of ln r. Okay, so I am taking this part as common, and it becomes ln r1 minus ln r, and ultimately we can write that using the basic logarithmic formula. It can be written as ln r1 divided by r. So this is your general equation which you can observe. And if you try to move on with this equation, if you try to change this equation in the dimensionless format, then it will be simply like this: t minus t1. So I am taking this here, and I will divide this equation by this term. So it will be t minus t1 divided by t1 minus t2, and it will be like this: ln of r1 divided by r divided by ln r2 divided by r1. So here you can find the dimensionless format. Okay, so this is the temperature distribution, but this is the dimensionless format which we are talking about. Okay, so this is your general equation, and this is your dimensionless format. So by this equation you can calculate the temperature at any instant and at any space within the cylinder. So this is your temperature distribution within the cylindrical wall. Now we'll be interested to find the heat transfer through this cylindrical wall. So from Fourier's law, you know that the heat flux will be proportional to the change of temperature gradient in the radial direction. In the radial direction is specified because of the cylindrical coordinates. So we are discussing the heat conduction for the cylindrical coordinates. So here the heat is transferred only in the radial direction. So this heat flux which we denote by this term will be something like this: minus k dt with respect to dr. Remember that we have done similar thing in the cases of rectangular slabs or the plane walls, where we have taken the temperature gradient, the change of the temperature gradient with respect to the direction, okay, or the length or the thickness of the plane wall. Here we are taking the temperature gradient with respect to the radius, okay. And since we have assumed a constant area throughout, we can multiply this heat flux with the area, and thereafter we can find this heat transfer rate. Okay, so remember that this Q provides you the heat transfer rate, not the heat transfer. Heat transfer rate means heat transfer per unit time. So it's better that I provide a dot here. Q dot means dq dt. Okay, the unit of Q dot will be in watts. So now we need to know this dt dr. So we have this formula from Fourier's law. We can generate this formula and we can calculate up this heat transfer rate within the cylinder. But the unknown is that we don't know the value of this dt dr. But we have this temperature distribution with us, and we need to derive this equation. So it will be very simple. You know that here this T1 is not a term which involves R. The term which is only involved with this R is this one. So we can write T. So I am not writing this temperature distribution once again. I will rather write the differentiation. Okay. So dt dr will be like can be calculated something like this. So dt dr will be like this: t1 minus t2. So this is obviously an constant, because this function will not change with respect to r, since there are no terms which involves r. So but you will see that if we reduce this term, if we expand this term, we will see ln r1 minus r. So let us take this minus ln r as the only term which involves r. So this part is constant, so there is nothing to worry about, so it will be T1 minus T2 divided by ln R2 by R1. So it will be ln R2 by R1. And if we uh, do the differentiation of ln R, you know it is very simple, and the end result will be minus 1 by R. So ultimately you get the differentiation result as T1 minus T2 divided by ln R2 by R1 into minus 1 by R. Okay, so this is your value which you need to put here. Okay, so putting this equation here, so Q can be written as K. Now this area is already given here. A is equal to 2 pi RL. Okay, so R is the radius in which we have taken the temperature distribution. We have assumed that this is at a radius R, which is obviously our assumption. Once again I am saying that this R at R can be taken as different values. If you want to find out what is the temperature distribution from the center of the cylinder, okay, then you need to know the radius. You do have a value of R, and you can put the value of R, and thereafter you can get the temperature distribution. Similarly, we will take this area, okay, the area of the cylinder as 2 pi RL. Okay, so remember that heat is transferring in this direction, so this area is here concerned, not this areas. Okay, so the circular areas which would have been 2 pi R square, they are not considered here because heat is transferring only in the radial direction. Okay, so this is why this 2 pi RL area has been considered. Okay, and we can write the value of dt dr now, so which will be T1 minus T2 divided by ln of R2 my R2 divided by R1 into minus of 1 by R. So now you can see this R and this R, they are alike terms, and this minus and this minus, they will end up with in the positive result. So I can just remove this, and I can remove this, and I can remove this also. So ultimately you find the heat transfer rate, which is defined by Q dot, is 2 pi KL. So I will like to write this K here, and I will like to remove this K from here. So ultimately you find that this heat transfer rate is 2 pi KL into T1 minus T2 divided by ln R2 by R1. So let us clear this whole things because it is getting too much messy out here. So I would like to clear up all these things, and here you can see the above one, this equation represents the heat transfer within the cylinder. Okay, the heat transfer at which this because of this temperature difference at the inner radius, and because of the temperature T2 at the outer radius, the heat transfer which is taking place, the heat transfer rate can be calculated by this formula. So it doesn't depend on the radius. Okay, so this is an important observation here. It doesn't depend on the radius. It is the inner radius and the outer radius, inner radius, outer radius, and the temperature difference. Obviously thermal conductivity is there because it is a material property, it is a transport property, it depends on the nature of the material. So this gives you the heat transfer rate within the cylinder, and this provides you the temperature distribution formula within the cylinder. So putting the value of R, you can get the temperature at any instant. Okay, so I hope that you have understood these concepts, and with this understanding, let us take our discussion a little bit further, and let us apply this concept to in the electrical analogy mode. So you must remember the electrical concepts which we have discussed a lot in the cases of plane walls. Similarly, here we can write this same electrical circuit, where you will see that because of this temperature difference there is a presence of a certain flow quantity which we know by Q, and there will be a thermal resistance present here, and this thermal resistance will be can be denoted as, you can understand that it can be written as ln R2 divided by ln R1 divided by 2 pi k L. So I think it is quite simple to understand, because you have the understanding for the plane walls. Now I'm sure that you are getting this, because this Q will be can be referred as, if you remove this, it can be referred as like this, and you know it is somehow similar to the Ohm's law of resistance, where I is equal to V1 minus V2, I'm sorry, so it is V1 minus V2. So because of this potential difference, the electricity transfer takes place, and here because of the temperature difference heat transfer takes place. So this is your electrical resistance and this is your thermal resistance. So thermal resistance in the cases of cylinders can be found as this. Okay, so with this understanding, let us take our discussion a little bit further for the composite cases. So if you find that there is a composite arrangement of the cylinders, then what is the process to calculate the heat transfer or the temperature distribution? So before starting the discussions on the composite cylindrical walls and the use of an electrical analogy to calculate the net thermal resistances, we would like to take you through a different topic, and then we shall move on to the one-dimensional heat conduction for the composite cylindrical walls. The thing is that sometimes you will find that this heat transfer rate through the cylindrical walls can be also expressed in the format of heat transfer through the plane walls, and in that case we have to take a mean area of AM and the thickness as R2 minus R1. My mistake here, as I have kept R1, so it will be R2 minus R1. So here you can see I have written the formula of heat transfer uh, for a plane wall which has a thickness of R2 minus R1 and an area of and mean area of AM. Okay, so using that formula I have written down this equation, and this is your heat transfer rate for the cylindrical surfaces which we have just calculated. So now if we equate this to equation, obviously we have written the same equation, so we can write this QP dot is equal to QC dot. So what I am trying to say is that we are writing the same equation but using two separate formulas. This equation has been written by using the formula of heat transfer rate through the plane walls, and this is the derived formula which we have just now seen for the cylindrical walls. Since these two refers to the same heat transfer, we can write QP dot equal to QC dot, and since they are same, they can be equated by this formula. If we equate these two formulas, then we can observe that AM by R2 minus R1 would be equal to 2 pi L divided by ln R2 by R1, and thereafter you can see AM can be written as 2 pi R2 minus R1 into L, which refers to the differences in area divided by ln A2 by A1. Now you must be wondering how this can be written. I think you know that A2 is 2 pi R2L and A1 is 2 pi R1L. So simply if you divide these two, you will get R2 by R1. So you can write this also. So the thing which I am trying to say is that this mean area is now expressed in this format. Okay, so I would remove all these things here. This mean area, I would write the mean area which we have derived, a2 minus a1. Just give me some time because I'm very sorry for my poor handwriting. A2 minus a1 divided by ln a2 by a1. So here, as I was mentioning you, this is a mean area, and we define this mean area as LMTD. Okay, uh, or we can sometimes say as logarithmic mean area. Okay, so this is logarithmic mean area. This area is called as logarithmic mean area. Okay, so when we are trying to equate the two equations, two heat transfer equations, one in the formula, one in the first case where I have expressed the formula in terms of plane wall, and in the second case where the general formula of cylindrical surfaces have been written, we can see this concept of logarithmic mean area have been generated. Now in most of the cases, like in the expressions of heat exchangers, you will find the application of this logarithmic mean area in a very vast way. So for that part, I was insisting to discuss this topic. So now, since we have understood the concept of logarithmic mean area, we shall move on to the one-dimensional heat conduction in composite cylindrical walls using the electrical analogy. So let us start that. So let us start our discussion on the composite cylindrical walls. So it is quite evident that the exact heat is being transferred through the different cylinders. Okay, now you can see it is a composite cylindrical walls. That means these cylindrical walls have been created by the help of different materials which have different thermal conductivity, obviously. So you can see this K1, K2, K3, they refer to the different materials. Okay, so this is a hollow cylinder which has several layers of insulation. It is you can assume that it is an insulation of a certain material, and then it has two other layers of insulations also. Now the heat transfer is going on in the radial direction, which can be written by this formula 2 pi k1l. For this material I am writing it 2 pi k1l t1 minus t2 divided by l1 r2 by r1. For this one, the same heat is being transferred, so you can write this formula 2 pi k2l t2 minus t3 divided by ln r3 by r2. And for this one, for the third material, where the same amount of heat is being transferred, you can write this formula 2 pi k3l ln r4 divided by r3. Obviously this refers to the r4. This distance is your r4, and this distance up to is r3, up to this one is r2, and this one is r1. So the radius are defined as this is r1, this is r2, this is r3, and this is r4. I think you have understood it. Okay, so using these formulas we have generated this. Now if you remember the concept of thermal resistance which we have discussed, it is the temperature difference divided by thermal resistance. So it is quite obvious that for the first case, for the first material which has the thermal conductivity of K1, it would have the thermal resistance L1R2 by R1 divided by 2 pi K1L. Now using these concepts of thermal resistances, there would be three separate thermal resistances. So I can draw a series circuit which have the end temperatures as their end points or the different points. So T1, T2, T3, T4 are the separate ones. So here you can find it, and Q is the flowing quantity. Okay. So with the help of thermal resistances we can draw this circuit, and we have found a series circuit which represents the case of these composite cylinders. Now, if we are interested to find the heat transfer rate in terms of the boundary temperatures, that is T1 and T4, then what we need to do is we can represent this T1 minus T2 as Q. That means that we have to represent this T1 minus T2 in terms of Q. Similarly, T2 minus T3 in terms of this one, and I'm sorry, I have missed here. It would be T3 minus T4. Sorry. Please rewrite or recheck your notes. If you have missed it, then please write it here. So what I was trying to say, that we need to express this heat transfer rate in terms of the boundary temperatures. That means the temperature of the innermost cylinder and the outermost cylinder. Then it is simple. What we would do, we would write just give me some time, I will clear this up so you can understand it in a better way. So it would be T1 minus T4 divided by sum of thermal resistances. You know that these things because this is exactly similar to the analysis of the plane walls. So when we were discussing this for the composite walls, we had generated this similar kind of formula. Here it is exactly same, but the terminology which expresses the thermal resistances, they have been changed. Okay, so you know how many resistances are present here. There are three resistances: RTH1, RTH2 and RTH3. You just need to add it up. So whenever you find in a mathematical problem the innermost cylinder temperature and the outermost cylinder temperature is provided to you, then you can easily imply it. Now what happens if we consider a hollow cylinder and you find that there is a fluid flowing over this cylinder? That means there is a fluid motion going inside of the cylinder or outside of the cylinder. So obviously it incorporates the convection heat transfer. So in that case you have to consider the thermal resistance because of the convection heat transfer. And you know what is the formula of convection heat transfer. You know that Q can be written as so just give me some time. It is Q convection H into area into temperature differences. So using this formula, you know that it can be written as delta T by 1 by HA. So this 1 by HA term is your thermal resistance because of the convection heat transfer. So depending on the problems, depending on the nature of the heat transfer, this HA 1 by HA needs to be added up with this net thermal resistance, and then only you can address the issue of fluid motion or the convection heat transfer caused by the fluid motion inside or outside of the cylinder. So that depends on the problem. It would be mentioned in the problem the nature of the fluid motion, where the fluid motion is carrying on, and how the convection is carried out. So the basic concept is that if there is heat transfer, then there is thermal resistance. And if you want to find out the heat transfer in the terminologies of the innermost cylinder temperature and the outermost cylinder temperature, then you have to add up all the resistances. And the other one is that always the heat transfer rate is always same. So whenever you are dealing with a composite cylindrical wall, then you must consider that the heat transfer rate is not going to change for whatsoever. It will be same for all the cases. For all the cylinders it will remain same. Say for the first one, for the second one, for the third one, if there is convection included, no matter, don't worry, the heat convection would be, the heat transfer rate would be same for each of the cases. So with that, I hope I would end up my lecture today, and in the next session we'll be taking some numerical problems and deal with that. And in the next session I would provide you some assignments regarding the one-dimensional heat conduction problems for the plane walls, as well as the one-dimensional heat conduction problems for the cylindrical walls. So I would like to end my lecture today here, and so let us wait for the next lecture. And thank you and goodbye all for your presence. Thank you.